So let's now turn to discuss some equations, ordinary differential equations that are very commonly encountered in science and engineering applications, and many of these equations we can call celebrated ODEs. They are arising in many contexts, and many of them have famous names of mathematicians and scientists associated with them in the context in which they arose. So let's start by looking at equations describing a single dependent variable y, and we have seen this equation before. Y dot equals alpha times y. Alpha is a constant. We can call it an equation describing boom or bust depending on the sign of alpha. If alpha is a positive number, then the solution to this equation would correspond to an exponential growth or boom. If alpha is negative, then it corresponds to a solution corresponding to a bust or an exponential decay of the quantity y. The second equation here, which is a second order equation, my double dot plus cy dot plus ky equals f of t on the right hand side, is again a familiar equation describing vibrations, oscillations in a variety of contexts, from mechanical to electrical to other systems. Let's now consider some more examples of second order differential equations. Here we are changing the notation a little bit. Y, the dependent variable, is a function of x, which is an independent variable. Previously we had t as the independent variable. In many contexts people traditionally like to write dependent variable as a function of x, and the context will make it clear why sometimes x is chosen to represent the dependent variable when it does not have the meaning of a time, but x would be more like a space coordinate, a position in space, and so on. So in this case the derivative of y with respect to the independent variable x is going to be denoted by y prime. All right, so we have three equations that are listed here. Let's take a look at each of them at a time. This equation, a second order differential equation, is very famous, and it's called the Bessel's differential equation. And this equation arises in the context of drum vibrations, for viscous flow in a round tube, as well as for heating and cooling of a rod. So many different contexts that involve circular geometry, flow through tubes, vibrations in tubes, and so on, also have the same equation showing up. The second example here is an equation which is called the Legendre differential equation. This involves one parameter n, which is an integer valued parameter for this equation to be called Legendre differential equation. And this equation arises in also a wide variety of contexts, all the way from tides to quantum mechanics and many things in between, such as oscillations of bubbles, oscillations of spherical shapes, such as oscillations of stars and the sun. Certain aspects of it involve this particular differential equation. Finally, let's consider this equation, which is called the Chebyshev differential equation. Note that the leading order coefficient here is the same. This is very similar, but this is now not n times n plus 1, but it's a positive number alpha square. This equation arises in numerical analysis and in problems involving in study of statistics, and we'll see some of these contexts later on, and we will learn about how to solve these differential equations and what are properties of solutions associated with these differential equations and how do we make use of them. Of course we won't be focusing a lot on the application, but the applications naturally produce these equations, and it's useful to know about these applications. So now we will extend our discussion to look at some nonlinear differential equations, some famous nonlinear differential equations, a small sampling of it. And so let's start by looking at this equation called the logistic equation. This is for a single dependent variable y, whose rate of change is given by this particular right hand side, r times y times 1 minus y. Typically r is a positive number, and this equation arises in context of population dynamics and in economics. To get a little feel for this, we can think about the solution, how it may behave. Suppose y is small, then we can approximate this term as being 1 here, and so this will correspond to growth of some population. But then this factor here represents constraints that are present in the system. Resources are limited, therefore the rate of growth is going to be constrained by that, and that will then cause some change and equilibrium of the population as it grows. So that's one particular context. We will look at equation like this and its variations later on. Looking at the second equation here, it's called the van der Pol equation, and it is an example of what is called nonlinear damping. So let's look at the equation. It corresponds to the dependent variable is u, the time dependent variable, two time derivatives. This is the derivative, first derivative multiplied by this coefficient here, and this coefficient depends on the solution u itself, and so this is a nonlinear term, and we can think of it as a nonlinear damping, and this is the spring term, if you like, plus u equal to 0. And so the behavior of this we can anticipate for the solution. If u is small, then we can see that this can be neglected here, this u square can be neglected, and since there's a minus sign here, this corresponds to negative damping or growth, instability in the solution. So this oscillation, which is a solution to a second order differential equation with constant coefficients, which is what we will have when u is small, is going to grow. As it grows, we can no longer neglect this u square in here, and so this will reduce the coefficient here, and in fact that will cause the solution to stabilize, and that's a behavior which is called nonlinear damping, and it's a common example of mechanical systems where this kind of behavior happens. Okay, we will now look at some nonlinear systems of ordinary differential equations. Two examples that are quite famous. The first one is called the Lotka-Volterra equation, or the predator-prey equation, and it's this coupled system. X and y are the two dependent variables, and the rates of change of x and y are given by these two right-hand sides. X denotes the population of prey, and y denotes the population of the predators. And as you can see, according to the sign of these coefficients, if a is positive, then the population of prey is going to grow, but then as the prey population grows, predators are going to take them out, as it were, and that will then allow the predator population to grow, because now they are feeding on the prey, and that will prevent them from extinction. And so the predator and prey are in equilibrium by sort of exchange of their populations and so on, one feeding on the other through this competition. And so this kind of a model is a common situation that arises in a competitive environment. They may not be predator and prey species per se, they may be chemical species, or they may be other physical variables that behave in this kind of dynamic way. So this kind of an equation arises in many contexts, and it's useful to learn about such systems and how we deal with them. So finally, we want to look at a relatively modern set of equations. These are very cool set of equations. The Lorenz equations, as they are called. These equations have been around for about 50 years and have already found a lot of fame and use in many applications. They describe the evolution of three dependent variables, x dot, y dot, and z dot here, which depend on x, y, and z. They were originally described or derived to describe the evolution of thermal convection, but such systems can be used to describe chaotic behavior, and they show very, very interesting dynamical behavior called strange attractors. Solutions depend very sensitively on initial conditions, and so you may have heard about the so-called butterfly effect. So equations of this kind have provided a foundation for understanding how chaos can arise in an otherwise deterministic system, and that has been a very significant advance in mechanics and dynamics and physics, and of course with widespread applications in economics and many other contexts that may not be in physical sciences. Use of such mathematical models in describing the physical behavior. So with this, we will close this discussion of famous equations. We have seen how we can classify the equations. We have seen some particular examples of equations with particular types of behavior. So what we will do next is we will turn to a more systematic study of ordinary differential equations and solution methods that can be used to provide a way for you to understand what the outcome of these differential equations would be. And of course, as we go along, we will provide interpretations of those solutions from a physical context as well.